Hi, everybody, and welcome to Team Science. We know that the space shuttle takes astronauts into space, but did you know that it also has taken toys into space? That's something that we'll be investigating in today's program, so get ready to blast off. Thanks for joining me today, and welcome to Team Science as we continue to explore forces in motion. I'm Judy Seidner-Gordon, your Team Science Studio teacher, and this is Program 4, Toys, Force, and Motion. In today's program, we're going to be taking a look at investigating how toys move. Also, we're going to observe some toys in space in an actual space shuttle, and we'll talk with a toy engineer to see how toys are designed. And finally, you'll have a challenge to design your own toy. So we have lots to do today, and we have two enthusiastic studio students with us. I'd like for you to meet them. We'll start with Malia.
Hi, my name is Malia Kabar, and I go to Linda Vista Elementary School, and I'm in the 5th grade. And I'd like to say hi to my teacher and classmates.
Okay, nicely done. And Sam?
Hi, my name is Sam Ettenschall. I'm in the 6th grade. I go to the South Pasadena Middle School, and I'd like to say hi to all my friends and family watching this.
All right, thanks so much. Well, welcome, and thanks for joining me today because we're going to have lots of fun. I have a toy here, and this toy moves, and we can maybe get a close-up here. I'd like to show all parts of my toy. All right, that's the back of the toy. Okay, there's the front of the toy. Now, what I'd like you to do is to think about this. How can we make this toy move, and what forces are involved? Now, I want you to think first and then share your ideas with a partner. And when we come back, we'll take a closer look at toy movement and forces. It's your time to think. All right, welcome back. So what did you think about my toy and how it moved? Let's take a real close look here and see what we have. First of all, I'm going to wind my toy up. And Malia, what does that do?
It stores up potential energy in the wind-up place.
Okay, it stores up the potential energy here. And of course, I use the force, pushing force to push the key, don't I? And then the next thing I'm going to do is to push this lever. There's a little lever here. I'm going to also use a pulling force to pull the lever to the side. And Sam, what else do you notice? What other kind of force?
When you pull the lever, the potential energy stored up is released as kinetic energy.
Okay, the potential energy is released as kinetic energy. And what else do we notice here? I had to pull him back. What about his movement?
On the paper,
it's a friction force,
Yeah.
huh? Friction force allows my robot to move on the paper. And I'm going to turn him off now, and what keeps him on the table?
Gravity.
Gravity. So we've got several forces involved just in one toy. Now, what you're going to do in the next activity is to investigate a toy of your choice. You want to find out, make some observations about your toy first, and then think about how that toy moves and do some investigation on your own. This is what your activity sheet looks like. So you can indicate your toy's name here. You're going to describe how the toy is designed to move, and then let us know what the forces are that you use to make the toy move. And there are a couple of other questions that you can answer as well. So why don't you go ahead and get started investigating a movable toy in your own classroom. It's your time. Now, Malia and Sam have lots of information about the toys that they've been investigating. So, and I know you've been investigating toys in your classroom too. I want you, first of all, to know that you can always share your observations, your ideas, and your investigations with me through the electronic classroom or by email or fax. And your teacher has all that information to share with you. But let's see what Malia and Sam found out. Malia, let's start with you. Tell us a little bit about your toy, and then tell us about how it's designed to move.
Well, I have a little orange cat on wheels.
Mm-hmm.
And when you push it forward, the wheels start moving. And then when it has contact with a surface, it moves because the wheels are moving.
Okay, and why don't you demonstrate that for us? All right, so you said something very interesting about the wheels on underneath your cat. Maybe we can get a close-up. Can we get a close-up of the underside of this toy? All right, you said something about these wheels. What did you tell me about the wheels?
These wheels have little dents in them.
Like ridges, huh?
Yeah. And so it gives the cat more friction.
More friction when it comes in contact with the surface.
Mm-hmm.
Excellent. Sam, let's hear about your toy over there. What did you call that?
I called this the pushable jet.
The pushable jet, okay. And Sam, tell us, how is that toy designed to move?
Well, I called it the pushable jet because you push down on it.
Mm-hmm.
And when you push down on it, it makes the front wheels,
Come out?
come out, yeah, which coils a hidden spring inside of it,
Uh-huh.
and that stores up potential energy.
Okay.
And when you let go,
Okay, you can go ahead and let go.
the wheels come down. The spring releases the potential energy as kinetic energy,
Okay, you can try that
and the
out.
back wheels move.
Okay, so, and that's really interesting. So it stores the energy and then releases it, right? Okay, that's pretty interesting. What's similar about both of these toys? What do you think? What's similar?
They both have wheels.
They both have wheels. Very interesting. Any other similar points in terms of energy?
They both move.
They both move, and they
Like-
both use kinetic energy
Yeah.
to move, don't they?
They both
Yes.
use kinetic energy.
Okay, excellent. Excellent. Let's go down here to the last question, because I think this is very interesting. And using what you know, talk about how this toy keeps moving. What does it need to do in order to keep moving?
The wheels have to keep moving so the toy keeps moving
Okay,
because the wheels push on the
push on the surface.
surface to move the toy.
Okay, so, and when those wheels stop moving,
The toy stops.
the toy
moving.
stops. And Sam, what about yours?
Well, this moves by the potential energy in the spring,
Uh-huh,
and when the energy runs out in the spring,
uh-huh.
it still can move just a little bit on inertia,
Okay. And then
and then it stops.
it stops. Now, we've talked about gravity, haven't we?
Yes.
Okay, and we've talked about gravity in previous programs. What do we know about gravity? Malia?
Well, it's a force.
It's a force. Sam?
It pulls things towards the center of the earth.
Pulls things towards the center of the earth. And I like that demonstration that you gave, because as you dropped it, it fell right down. Isn't that correct? Okay. Well, we know that gravity does do that here on Earth. But in space, there's not much gravity, is there?
No.
No. Well, you know, there are actually some toys that have been taken up in the space shuttle. You've got some of those toys in your kit in the classroom. Let's take a look at what some of them are here on my overhead. I've got just a few of them here. There were magnetic marbles that were taken up in space. See how those work? They also took a paddle ball up, and they took some wind-up toys too. Now, they didn't necessarily take a frog like my frog here, but they did take some wind-up toys in space. In this next Your Time activity, what you're going to have a chance to do is to investigate these toys. How do these toys work in your classroom, and then how do you think they will work in space? I want you to think about it and do some observations and do some investigations and really give some good thought to what happens to those toys in a microgravity environment. Here's what your activity sheet is going to look like. Do part one only. That's this part up here. Write down the toy's name. Again, write down how it's designed to move. And then finally, write about how you think this toy would move in an environment that has less gravity than we have here on Earth. So go ahead, work with your partners, and investigate the toy and think about how it might move in space. It's your time. Now, Malia and Sam have just finished up their activity sheet, and what we're going to do first, though, even before we share with you what they found out, I'd like for you to take a look at this special videotape about how these toys actually behaved in space. Take a look. In this microgravity environment, when the astronaut throws the basketball into the basket, will it go through the net? Let's see what happens.
When you throw the basketball, will it go the same way I aim it? Well, when you throw a basketball on Earth, you have to worry about throwing it in an arc so that it will go up and gravity will pull it back down and go into the hoop. Here in space, whatever direction I throw the ball is the direction it's going to go. If I throw it that direction, that's the way it goes. If I throw it up this way, that's the way it goes. So yes, the ball goes in any direction that I throw it.
Do you think that there is magnetic force in space? These magnetic marbles are similar to the ones you have in your classroom. Notice how the marbles attract each other and form a line. Pushing the center of the line in one direction, causing the ends of the line to attract each other, forming a circle. This is Endeavour mission specialist Susan Helms. She's holding a wind-up toy submarine. What do you think will happen when she winds up the toy and releases it?
Here we go, Chris. Okay, remember when I talked about the winding mechanism inside the toy? That's what we had here. We had a toy that had a very strong wind-up coil, but the toy itself, in air, doesn't propulse very well. So we ended up having the toy just turn on itself as it began to unwind.
This is the entire crew of Space Shuttle Endeavour with Commander John Casper.
So we'd just like to remind all the folks that are watching out there that, especially the children, that science applies to everything, even toys. And we hope that our demonstrations today have given you just a taste of scientific research in space. And we want to encourage all the children out there to do well in science and math and to learn all you can about the world around you, because we need people like you to design and maybe even fly the experiments of the future. So as we say goodbye, we're going to release all of our toys at once. 1, 2, 3, now. Okay. Bye-bye, everybody.
I just find that so fascinating to compare and to see how some of the toys that we are familiar with right here on Earth operate in that microgravity environment, what they do and how they behave. Very fascinating. Well, what I want you to do now is to continue on your activity sheet with part 2. And then when we come back, we'll have some further discussion about the toys in space. It's your time.
this page.
Okay. All right. Now, Sam and Malia have been finishing up their activity sheets here, and one of the things that we have found out is that it's very interesting, some of the differences between how these toys behave on Earth and what they do in space. So Sam, you had the magnetic marbles. Tell us a little bit about that, and I'm going to bring your activity sheet over here so that you can actually explain some of the things that you found out. Go ahead and describe this to us.
Well, I made a top view and a side view of what would happen in space and in the classroom.
Okay. So let's start with the classroom view here.
In the classroom, when you push the marbles together, they will link to each other, and they will just
do they stay
on
in
the
that line?
tabletop.
Okay,
They'll stay on the line. They'll stay on the tabletop because there's gravity on Earth.
Okay.
But in space, there isn't gravity. They would eventually link together by themselves, and because they're like floating and wobbling around, eventually the two ends would link.
So they form a circle then?
And they would float off the tabletop because
Okay.
there is no gravity.
Okay, excellent, excellent. And I like the way you've included the tabletop here to show us the difference of what happens on Earth and in space. Let's take a look at Malia's drawing here, and Sam, I'll give you your paper back. Here's Malia's paper. Malia, let's take a look here at your drawing. Now you had the wind-up frog. Tell us what's happening here in the classroom side, and then explain to us what's happening on the in-space side.
Well, the frog in the classroom would just be on the table and wouldn't be floating around because there is gravity, and would move sideways because it can't really do anything else but move sideways.
All right, and I noticed here you put the wind-up stem right here. Excellent. So you showed us that it will just move across the table in one direction, right?
Yeah.
Okay, what happens in space?
In space, it's all floating because there's no gravity, and since the little thing to
The winding
the winding part,
stem? Okay. It turns?
Once you wind it up, then it has to unwind. So when it unwinds, the frog turns around because it's not on a tabletop.
Okay. It turns around the winding stem? Now that's pretty interesting, isn't it? I think so. So that's very similar to the wind-up toy that we saw in the video, isn't it?
Yeah.
And Sam, one of the things that we've talked about with the magnetic marbles, what happens when you apply the force that the astronaut applied? Remember he kind of flicked the marbles apart? Why don't you try that and tell us what's going to happen?
Well, on Earth, I think there's like something
What
that
happens when you...
makes the magnetic force weaker, and it's easier.
Whoa!
Whoops.
It went all the way off the table. But what happened? It actually broke apart, didn't it?
It's easier to break it apart.
Okay.
Meanwhile, in space, if you do that, it would just flop around.
It flops around, and eventually, as you said, what happens?
Would link together.
The two ends come together and they link. Those were excellent ideas. Now, I'm sure you found some similar things out in your classroom where perhaps you were working with some different kinds of toys. At any rate, let me know what you found out, either in the electronic classroom, by email, or by fax. Well, let's come back to Earth now and think a little bit more about this toy thing. You know, there are people who have jobs designing toys. What I'd like for you to do is to share with a partner your ideas about how a toy gets from an idea in a person's mind to the shelf at your local toy store. You'll have about 2 minutes to share. It's your time. I know you've had some really interesting ideas out there, but I want you to come along with me on a video field trip. We are actually going to talk with a toy engineer. Listen to what he has to say about designing toys, and listen carefully to what he has to say about the forces involved as he designs this toy. Take a watch and listen.
My name is Mike McKittrick. I work for Mattel Toys, and I'm a toy engineer. I work in a department called D&D, which stands for Design and Development, and over there we engineer toys. A toy designer basically works on the visual side of the business. A designer works hand in hand with an engineer. The engineer actually does the actual drawings, the dimensions, and actual refinement of the parts that go into a toy, but the designer is what gives the engineer the look of that toy. We use science all the time. When we work on mechanical toys, like the one I'm going to show you today, we deal with gears and wheels of different sizes and mechanisms, motors, levers and cams, and with that, and with the right combination of parts, we can make things move in a variety of ways. We use forces all the time to determine how much a toy moves and maybe how fast it should go. This particular toy was done in a line we did several years ago. It started off as a sketch in somebody's mind, and with that, the idea was to have a large vehicle in the form of an insect that walked. And to do that, we went through several steps. The first thing was to do a little bit of research and find out how do insects walk to start with. In that, we found that a typical insect, which has 6 legs, they move in such a way that 3 legs are always on the ground. And to simulate that, we started looking at wheels and levers and cams and such. And we found that by having a wheel, we basically added a cam. And this particular cam that we added to it, as we attach it to here and connect the pivot point here, it gives the motion a different pattern. Instead of a circular motion, it gives a true D type of a pattern, which is exactly what we wanted, where it moves across the ground, it lifts up, goes to the front, and goes across the ground. This, to us, is more realistic. The next step was to prove out our idea of using the wheel and this cam into a mechanism with the leg to simulate the leg walking. And with this model that I'll show you, you can see what we've done. This is the exact movement that we're after. You can see the bottom of the leg moves across the bottom, and then it lifts up and goes to the front. The next step for us was to engineer that into a complete large insect, okay, with 6 legs to see how that would work out. Of course, the legs have to be synchronized, so we always have 3 on the ground at one time. And with that, we built this prototype model, and it took us several models to get to this stage, okay? This demonstrates the toy that we'd like in the final design. You can see the rowing action that takes place within the gear train here and how it relates to the leg. One of our interesting findings as a result of testing this prototype is that we found that the batteries lasted over 8 hours on this toy. Our requirement is only 3 hours. What we found is that because of the arrangement of the gears and the way it's reduced down to the number of gears we have is why it was made so efficient. That was our next step. Once we were happy with that, we basically engineered the toy on paper, a complete engineering layout. At the same time, we also want to get it costed to ensure that it's going to be within the right cost parameters that our marketing people would like to sell this toy at. Then, getting to the final product, working with design hand in hand, this is what we came up with. This is called Spider. As a child, I've had many hobbies and interests. I used to build model car kits. I've had chemistry sets and microscopes, and I've always loved science. Out of high school, my interest grew there as well. I've taken architecture. I've had some art classes and some electronics as well. I guess as a result, all of this combined led to my current career as a toy engineer. Perhaps the interests and hobbies that you have now can lead you to a career that you would also enjoy.
That was pretty fascinating. If you'd like to find out more about toy engineers and what they do your own research. Search the net and see what you can find out. Let me know what you find out. Well, it's time for our next clue in the Science Sleuth's Bogus Break Challenge. Remember, there's a problem here, and you are helping the sleuths solve it. let's take a look at our next clue. Pay attention and take notes.
What kind of brakes do you use to slow down?
Brakes? Who needs brakes? I want to go fast. That's why I sand them and wax them. Sand off any unevenness that can catch the ground and wax them to keep it smooth. No friction between me and the snow. I point those skis straight downhill and go for it. Stop? I don't want to stop. Oh, hey, if I have to stop. I lean forward like this so my weight is off the back of the skis. Then I lift and thrust the skis to one side. Then the whole long side of the skis pushes against the snow. I only stop once for every trip down the mountain.
That's all the time we have for today. But for next time, what I'd like for you to do is to look for ways that objects interact, and then choose a bogus brake clue to share with me in the electronic classroom, by email, or by fax. And finally, be a science superstar. For your journal entry, what I'd like for you to do is to think about designing a toy of your own. How does it move? What forces are used to make it move? And then draw an illustration of your toy. Thanks for joining me today, and remember, science is taking a closer look at the world around us. Be a science superstar, and I'll see you next time.